Yeah, thank you, Manish, for the two awesome sessions. So now, so I'm going to talk about before coffee break. I'm going to talk about the reasoning data sets with LLM annotations, and after coffee break, I'll talk about evaluation of LLM generated annotations. So yeah, myself, so I'm currently a postdoctoral researcher in association with TU Berlin and UC Berkeley, under the guidance of Professor Fatma Deniz. And my area of research is mainly on intersection of language processing in human brain and language processing in language models. Okay, so now let's start the reasoning data sets with the LLM annotations. So I'm also
Hey,
going
Subba,
into
sorry, we
some.
can see the wrong screen. So you might want to switch the screen. Display settings, just go to display settings.
Yeah. Okay.
Yeah, awesome. Yep, this helps.
Okay, so I'm also going to introduce about some details of reasoning and what are the existing reasoning data sets in the literature. So what is reasoning? So reasoning is the human cognitive process of drawing conclusions, making decisions, and solving complex mathematical problems. So reasoning can be divided into multiple types of skills, as Manish discussed in the previous slides, like common sense reasoning, mathematical reasoning, symbolic reasoning, and also logical reasoning. So sometimes when we are solving a problem, so like we also use multiple inferences or multiple steps to reach out the conclusion. So we used to call it as a multi-step reasoning. So here is an example. So these are all the examples for the common sense reasoning. So common sense reasoning is like we use everyday knowledge and understanding to make judgments and predictions about new situations. So here there are like these are all like different daily examples, daily situations. The boy is kicking leaves, a woman is getting a train, the girl is starting a new school. So based on these situations, so we can come up with different decisions with incomplete information. So why a woman is getting the train, so where the woman is heading towards, so where she is going, so what could have like her bag, like what is there in her bag. So we can make different kinds of decisions even with the incomplete information. So these are all examples for the common sense reasoning. So this poses a question of, so we have different reasoning problems in the literature. So do current large language models truly understand and apply these reasoning abilities? So if you look at these reasoning problems, so arithmetic reasoning, so in arithmetic reasoning, it is the ability to understand and apply mathematical concepts and principles to solve using some arithmetic operations. So suppose in arithmetic reasoning, if you give a question, if there are 3 cars in parking lot and 2 more cars arrive, how many cars are there? So here we use addition as an arithmetic operation to solve this problem. So symbolic reasoning is also another form of reasoning that involves manipulation of symbols according to the formal logical rules. So here, suppose if you give a question, take the last letters of a word in Elon Musk and concatenate them. So here, the job is to follow the rules like manipulation of symbols. Take the last letters from each word and concatenate it. Followed by common sense reasoning, as I discussed in the previous slide, that common sense reasoning is the use of everyday knowledge and understanding to make the judgments and predictions. So suppose if you ask a question, what home environment equipment requires cable, and if you provide multiple answer choices, so we need to provide the answer as television. So television is a home entertainment and it also requires cable. So there are more harder language tasks, so which require multiple reasoning steps to solve these problems. So multi-step reasoning is often seen as a weaknesses in language models. So we have small language models and also larger language models. Small language models like BERT, GPT, or T5 models. So these models still lack the reasoning abilities in these models, because these models, these models are pre-trained models trained on some data sets, and if we take these models and tune it to specific data set. Let's say if we have arithmetic reasoning data set, if we have common sense reasoning data set, so we take this model and we do supervised fine tuning on these data sets, and these models have some task specific information. But what are the limitations with these approaches? So creating a reasoning data set, like with the explicit reasoning, it can be difficult and time consuming. So because humans have to write all the intermediate reasoning steps and to give the conclusion, so this is an arduous task. And also training on a specific data set limits application to specific domain, because in smaller language models, so every time we have domain specific data sets, we take the model and tune it to specific domain. So if we have n number of domains, we need n models. So reasoning ability may emerge in larger language models at certain scale, such models with over 100 billion parameters. So recently, all the large language models like LLaMa, PaLM, or GPT models, so these models are with over 100 billion parameters. And even the researchers state that these models have several reasoning abilities. So but still it is unclear what extent these large language models are capable of reasoning tasks. So here are some reasoning and common sense benchmarks. So these are the popular benchmarks whenever we have any large language model is created. So we evaluate these larger language models on these reasoning and common sense benchmarks. So these are some popular benchmarks. Under reasoning, we have HELSWAC and also BBH. So in HELSWAC, so we have all the common sense reasoning tasks. Whereas under BBH, we used to call it as a big bench hard. Under big bench hard, we have arithmetic reasoning task, logical reasoning task, and symbolic reasoning task. So here you can solve the complex math problems and even writing code, etc. So along with reasoning, so we also evaluate larger language models on language understanding, because so whatever the generated content, whether the generated content is true or false, so the benchmark is truthful QA. So in truthful QA, so the more we evaluate the models on their ability to provide, whether the model is providing accurate answer or whether or it is a false answer, because it is crucial for combating this misinformation, and it is also promoting for ethical AI usage. And also we have MMLU. This is a massive multitask language understanding. So whenever you train a model on data, so we want to evaluate what exactly the model is learning from the pre-trained data. So to evaluate the learning knowledge from the pre-trained model, so they use this massive multitask and they check the capabilities of the model. And if you can look at other benchmarks, like other domains like math, coding, conversation, logic, test. So under coding, so this is like a human evaluation. So in human evaluation, so the humans have like they have created so 164 like unique programming tasks. So this is mainly useful for evaluating models code generation. So these days, all the large language models, they've been writing the code in different languages. So using the coding benchmark, so we can evaluate the model's code generation capabilities. And if you can look at the other benchmarks, conversation, logic, tests, all under the chatbot arena and MT bench. So in chatbot arena, so we have two models, two large language models, but we don't know what those models are, whether it's a GPT-4 or Claude or Anthropic. We don't know what is the model, but we take always two models. And when a user query these two models, the two models generate the answers, and user will pick one of the answer as a best answer. And based on that, the chat arena platform rank these large language models. Whereas in MT bench, so in MT bench, evaluate the chat assistants, like there are multiple users participated in conversation, and here the LLMs act as a judges. So in chatbot arena, users are the judges, whereas in MT bench, LLMs are the judges. Okay, so now we have all these reasoning and the common sense benchmarks. So how can we assess these reasoning abilities in larger language models? So if we consider the GPT-4 technical report and on the performance on different reasoning benchmarks, so all over the models, when we compare the state-of-the-art models with the GPT-4, GPT 3.5, so GPT-4 achieved awesome performance compared to the state-of-the-art model. So it is having super performance on all the reasoning tasks. So while state-of-the-art models still struggle to get above 50% with pre-training, whereas GPT-4 models achieve a record like 95.3% on the common sense reasoning. So these are like everyday events tasks, even with just a few short, 10 few short prompting. So 10 short means like we provide 10 examples to the model, and the model during inference time, it achieves all the correct answers. Okay, so Manish already discussed about chain of thought prompting. So why these large language models have some level of reasoning abilities. So it came up with the idea of chain of thought prompting. So in chain of thought prompting, so chain of thought prompting is a series of intermediate natural language reasoning steps that leads to the final output benefit. So suppose, so normally in the standard prompting, so we have a question and directly the answer. So we don't know how the model reach out to this answer. So every time we have question and answer, but we don't have any intermediate steps to reach this particular answer. Whereas in chain of thought prompting, they not only provided the question, but they also provided the reasoning steps and they reach out to the answer. So the model is now learning what are the steps to get this answer. So with this kind of chain of thought prompting, so whenever they provided a new question, now the model is also providing the intermediate steps to reach the answer. So yeah, so like given a prompt, now the chain of thought model, so it provides the reasoning step to reach the conclusions. So keep in mind that the authors of this chain of thought prompting, so they mentioned that this is an emerging ability that arises sufficiently with the larger language models. So now if we can look at chain of thought prompting on all these reasoning tasks, suppose like arithmetic reasoning. So in arithmetic reasoning, so it's all about solving mathematical problems using some arithmetic operators. So suppose these are all the different mathematical problems. And also we have multiple choice questions, like given a mathematical question, and so there are multiple answers are present. So again, the model have to provide all the reasoning steps to reach what is the correct answer here. Similarly, like there are some system of equations, or what is the, if we give a by b equal to 3 by 4 and 8a plus 5b equal to 22, then find the value of a. So, and they provide different answer choices, then the model follow all the intermediate steps to reach the final conclusion. So how they have created this arithmetic reasoning data set. So manually composed of 8 exemplars, so 8 human annotators have created this particular data set with all these kind of different examples. So some are like multiple choice questions, some are like just a question followed by the reasoning steps. So 8 humans annotated this particular data set. So all contains equations with the flexible formats, like so they have provided different prompt templates and they have created with all set of equations. So benchmarked on a GSMK. So this is like a grade school math question. So like this data set contains more like a grade school math level problems, whereas SVAM, it is like simple variations on arithmetic math word problems. So elementary level problems present in the SVAM data set. And we also have MOPS. So it is like online repository of math word problems. So these are the 3 arithmetic reasoning data sets, and people evaluate. So what are the reasoning LLMs? So they evaluate on arithmetic reasoning for these data sets. So for the smaller language models, when they tune on these dataset specific, so they do not positively impact performance for the small language models, whereas with few short examples in the chain of thought reasoning, so they achieve better performance on LLMs than zero shot chain of thought reasoning. So if you can look at these, like chain of thought reasoning on these arithmetic reasoning data sets across all these 5 reasoning data sets. So we have this table reports standard prompting versus chain of thought prompting. So across all the reasoning data sets with the chain of thought prompting, there is a huge improvement compared to the standard prompting. So chain of thought prompting improves performance on range of arithmetic reasoning tasks. So now if we look at symbolic reasoning, so in symbolic reasoning, so instead of providing the numbers, now we deals with abstract symbols, because the model need to learn these abstract symbols and also need to learn the relationship between the concepts. So the tasks are like last letter concatenation and also coin flipping. So if we give a question, like a coin is heads up, Jamie flips the coin, Teresa flips the coin, is the coin still heads up? So when Jamie flips the coin, it is tail, and when Teresa flips the coin, it is head again. So is the coin still heads up? So the model also provided that whenever it is an even number, the coin stands heads up again. So the provided answer is yes. So in symbolic reasoning, so they also evaluate in-domain and out-domain examples. So in-domain means, so like in the last letter concatenation, so they always evaluate on two words. So every time they give two words and they ask to concatenate the last letters of two words. But in out of domain, instead of testing on the two words, so they also evaluate on three words, four words. So this is the one like disadvantage in the chain of thought prompting paper, that they've only evaluated. So when they tested on two words, they only evaluated on three words or four words. So they never evaluated on more than 50 words or like 100 words, because humans are like they self. So once if they learn some tasks, so they self-evaluate on the remaining tasks, if you give the similar kind of example. So even for the coin flipping, so they've only evaluated for a coin is heads up or two times heads up or three times heads up. They never evaluated on more than four times or five times heads up. So this is a one drawback of the chain of thought prompting model. So standard prompting fails out of domain tasks for the both tasks, whereas zero shot chain of thought prompting achieves similar performance. So compared to the few shot with the even larger parameter model. So also we have common sense reasoning. So in common sense reasoning, we have CSQA. It's like a common sense question answering data set. It is more like an explicit reasoning task data set. So in explicit reasoning, so whatever the questions we have, which are very clear and there is no ambiguity in the question. So what home entertainment equipment requires cable? The question is very clear. There is no ambiguity here. There are other tasks like a strategic QA. So in strategic QA, so these are more like implicit reasoning tasks. So like could Brooke Shields succeeded at University of Pennsylvania. So here, so the question, though it is not, it is indirectly presented the question, and there are some assumptions. So like we need to get some details that whether Brooke Shields whether studied at University of Pennsylvania. So we need some details to answer. So in strategic QA questions. So in common sense reasoning, so they have created different kinds of tasks, both explicit and implicit reasoning tasks. And also like second robot planning. So given locations, different objects and actions. So how would you throw away cup? So the plan is like find a cup, pick a cup, find trash, put cup, and done. So chain of thought reasoning shows some minimal benefits on common sense question answering and also strategic QA tasks, and few shot achieves better performance than zero shot for the common sense and strategic QA, but zero shot COT achieves significant performance for a data understanding task. So overall, if you see for the arithmetic reasoning and common sense reasoning, few shot achieves better performance because these are some complex tasks. You need to provide some examples and the model then performing well. Whereas for the task like symbolic reasoning or like simple data understanding, so for those tasks, even zero shot COT significantly perform well. So as I mentioned, there are some limitations in chain of thought reasoning. So how people can improve the chain of thought reasoning abilities. So there are more advances in the literature. So one is self-consistency. So self-consistency is an approach. So here we ask the model with some prompt, and we have a language model, and we ask the model to generate multiple answers. So the same prompt, same language model, but generate multiple outputs. So here, so like if we give a there is a one, this is a one shot example. So already one question with answer, and we asked another question. Now the language model generated multiple answers for the same question. So now if we can look at the answers overall, so there are two answers, we have the similar answer. So the majority vote will consider the final answer. So in self-consistency, so we are evaluating the model with multiple generations, and finally we reach the conclusion based on the majority voting. So self-consistency definitely improves, so significant improvement over the chain of thought prompting alone. So if you can compare the arithmetic reasoning and common sense reasoning, so self-consistency have improvement for the both arithmetic reasoning and also common sense reasoning task over simple chain of thought reasoning. So change greedy. So in chain of thought reasoning, we always get only one answer, whereas in the self-consistency, the model generate multiple answers, and finally we'll take the majority voting. So we also have self-taught reasoner bootstrapping reasoning with reasoning. So as of now, these language models, we always feed so some data with all the intermediate reasoning steps. But like humans, on the other hand, so they improve their reasoning abilities by self-thinking without external inputs. So whether LLMs are also capable of self-improving with the only unlabeled data set. Let's say you have an unlabeled data set, but there are no intermediate reasoning steps, then how model learn so these reasoning ability. So what they did, so they take a language model, and the data set they consider it is having both question and answer, but there are no intermediate reasoning steps. So the model always come up with some rational. So the rational is like some intermediate reasoning steps, and when it reaches the answer. So whenever the answer is correct, so then they take this rational and they again feed it to the, they prepare the training data. Whenever the answer is wrong, then the humans provided the rational and they added this rational as and with the answer, and again they feed it to the training data. So this is how now the model is learning itself the rational even on the unlabeled data sets. So here the model is generating the rational, and where for the incorrect answers, it takes the human help and it improves the rational abilities. So here, so this is the task. So like each series corresponding to accuracy of summing two n-digit numbers. Like if we take one, so that means adding two one-digit numbers. So adding two-digit numbers or adding two three-digit numbers. So without rationalization, so we need more iterations to learn model to get the better accuracy, whereas with rationalization, so the model even with the few iterations, it reaches the better accuracy. So self-taught reasoner, which iteratively improves the model's ability to generate rationals to solve this problem. And so even so human participants also, they prefer 74% that model generated rationals are better compared to the human generated rationals. So we also have program-aided language models. So instead of taking the natural language as a reasoning steps, like so here we always use only the natural language as a reasoning step. Instead, so provide the problem and code it. So provide the problem, the reasoning steps in the form of programming. Like Roger started with 5 tennis balls. Here we take tennis balls equal to 5. So we create variables and we follow the programming level and finally reach the solution. So if you follow the programming level of approach instead of simple natural language reasoning, so even the performance is much better on all the reasoning tasks compared to the chain of thought reasoning. So programming aided language models enhance problem solving by generating code to represent the intermediate reasoning steps. So whereas chain of thought reasoning, it uses only the simple natural language to reason the problem. So there are also problems like Tora. Tora is like a tool integrated reasoning. So here you can see they are combining both rational and also the programming aided language approach. So like here the rationals are like all the intermediate like natural language reasoning steps in the programming. So it is more like a programming kind of approach. And if you combine both in the loop, so here, so we have the rational, it is a natural language reasoning, and they also use external tools like some SciPy or something. So they use this programming output. So the model is even performing much better, the combination of both rationals and natural language reasonings. So if you take Tora, Tora is even performing much better compared to the prior models like GPT-4 or like other base models. So it is having better accuracy on all the reasoning tasks. So Tora models even exhibit remarkable improvements. So if you can consider both programming level of reasoning steps and also the natural language reasoning steps. So yeah, so it follows, we have a problem and the tool integrated reasoning. So here we have rationals and the tools are like external tools we can use and for generating the program. And so again, so if we use self-consistency, then we will get multiple outputs. And finally, we can take the valid output and we fine tune the model. So it follows the self-consistency, rational, programming aided. So all these three approaches are present in Torah, and the model achieves even better accuracy here. So utilize GPT-4 to synthesize these high quality trajectories on arithmetic reasoning data sets. So overall, how they have validated that which is a better trajectory one. So they use GPT-4 model to validate these high quality trajectories. So overall, yeah, so Torah provides, this is a very recent paper, and it provides future research work because it is combining all the advancements in the reasoning, chain of thought reasoning, self-consistency, everything. So we also have plan and solve prompting. So yeah, this is a popular approach, plan and solve prompting rather than just solving the problem. So first you decompose the problem. Like before solving any problem, first make a plan. What I have to solve. So what steps if I follow, I will reach out the solution. So here plan and solve prompting. So here, so what they do, first they make a plan. In step one I have to do, step two I have to do, step three I have to do, and so then solve the first step, second step, and third step, and finally reach the solution. So plan and solve prompting is like more like a plan and solve the problem. Yeah, so zero shot from plan and solve prompting even consistently outperforms zero shot chain of thought reasoning across all reasoning data sets by large margin. So, okay, so now we have seen that LLMs are also using for like augmenting the rationals and even validating the trajectories. Now, can we use these LLMs to benchmark these reasoning data sets? So with models like GPT-4, now it is possible to synthetically produce data sets more comprehensive and diverse than human labeled ones. So one particular benchmark is a critic bench. So critic bench. So in critic bench, the advantage is like we can check the like we can use language model to identify so like self-improvement of language models, like the language model itself identify what are the issues in the generated responses, and the language model itself again propose the what are the suitable modifications. So it acts like a critic and it also acts like corrections. So what they did, so we have all the reasoning data sets which covers arithmetic, symbolic, everything. And from these existing data sets, they randomly sampled some examples from these data sets like question collection. And so from these questions collection, they made the prompts which consist of all the reasoning tasks. And they have used 15 large language models, and each large language model critique the other language model, and also it suggests where they can improve. So, and we will get a valid responses, and these valid responses should be evaluated by one GPT-4 and finally the human evaluation. So for example, so they randomly select the examples from the like existing domains, and there are 15 data sets covering all these 5 reasoning domains. So the responses collections from LLMs, so they evaluated on various LLMs, and each LLM generate response for each question and also provide what is the valid reason for that particular answer. Response annotation, so response correction, so the correction will be performed more by GPT-4 and humans. So this is a sample example from the critic bench. This is a question and we have a solution. And so this particular solution, so exactly the answer is C. And if you follow rule-based answering, so it is providing correct answer, whereas GPT-4, it provided wrong answer, even human provided the wrong answer. So the final label is wrong. So GPT-4 evaluation is closer to the human evaluation in the critic bench benchmark. So if you can look at the consistency of generation and critic and consistency. So overall, so GPT-4 is working really well for all the language models. So GPT-4, it is critiquing every language model really well, and it is also generating. So if you can consider all the generation, critic, and correction, GPT-4 for all the 3 tasks, it is doing really well, whereas some language models only doing correction part well, but not the critiquing. So it is not giving any feedback or what are the errors in other models, but GPT-4 is doing a really good job for every language model that what are the errors, where the one can improve. So GPT-4 is really doing better job here for all the generation, critique, and correction. So overall analysis across different tasks, so that larger language models perform better both in critique and correction tasks on logic compared to those requiring attention in detail.